Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about angular momentum. Angular momentum is going to take its place alongside of energy and linear momentum as a quantity that has associated with it a great conservation law. We've previously talked about conservation of energy and conservation of linear momentum. Angular momentum is the third of the trio of important conservation laws that we're going to talk about in Physics 107 this term, and it's an idea that extends not only within the realm of classical mechanics, explaining things like, for example, Kepler's second law or the physics of a spinning ice skater, but also it plays an important role in quantum mechanics. So let's dig in. Okay, so to talk about angular momentum, it's good to have a specific example in mind. So we'll take as our sort of canonical example the example of a spinning bicycle wheel. And before we talk so much about the spinning bicycle wheel, let's remind ourselves what we already have seen in the case of linear momentum, because a lot of what we're going to see with angular momentum is going to be very analogous to things that we've already discussed in the context of linear momentum. So we started off many weeks ago talking about Newton's second law, and we wrote the second law for a point particle of mass m as F net is equal to the mass times the acceleration. And to keep things simple in today's discussion, we're just going to imagine we're going to end up talking about only about situations in which the orientation of the axis of rotation remains fixed. And that ends up being equivalent to limiting discussion to motion in one dimension. So I'm going to leave off the vector signs in today's discussion. So I can write the second law, Newton's second law, as F net is equal to m times dv dt. And if we're just considering a single particle where the mass is constant, I can move the mass inside the derivative and rewrite this as F net is equal to d by dt of m times v. And we defined the momentum of the particle as the product of the mass times the velocity, and that enabled us to write the second law as F net is equal to dp dt. Or another useful form, if you consider a short period of time, delta t, in which the force remains short enough so that the force can be treated as a constant, we have that the change in momentum is equal to the force times the time interval delta t. And we call this quantity on the right the impulse. And this statement of Newton's second law says that momentum is changed by a force acting over time, or an impulse. And this was important because if we considered systems that were isolated systems, so that there was no net external force acting on the system, then we had that the fact that the total momentum of the system is conserved, that it doesn't change over time. So that was conservation of momentum. And now we're going to see something very similar in the world of angular momentum. So we start by writing down, suppose we have a rigid body and we want to write down the analog to Newton's second law for a rotating rigid body. And we've written that like our bike wheel here. And the version of Newton's second law for rotating rigid bodies is that it's the net torque that determines the angular acceleration of the rigid body. Or more specifically, we can say that the net torque acting on the object is equal to the product of the rotational inertia of the object times the rate at which the angular velocity of the object is changing. Or if we consider the rotational inertia to be a characteristic of the rigid body and a constant, we can move I into the time derivative just like we did above, and we can write this law as the net torque is equal to the time rate of change of the product of I times omega. And we can now define this product I times omega, and we can call that the angular momentum of the object. Angular momentum, and we use the letter L to denote the angular momentum. So we have that the net torque is equal to the time derivative, or dl dt. And notice how this form is exactly mirrors the way we wrote Newton's second law for the case of involving linear momentum. And again, by analogy to what we did above, we can say that the change in the total angular momentum of a system is just given by the net torque on the system times the amount of time that that torque is exerted. So this is net external torque on the system. So torques acting over time change the angular momentum of a system. And most importantly, if there is no net torque on the system, then the angular momentum is conserved. So this is a statement of the conservation of angular momentum. No net external torques acting on the system, then the total angular momentum of the system will not change. And this is the basic physics that explains what goes on in an ice skater's spin and how they speed up at times during the spin to quite spectacular effect. And I don't think I can do this justice without showing you the following video clip, which was prepared by our friends at Rice University in Texas. So let's
Tireless
watch.
training. Skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Yes, angular momentum, how skaters become champions. Okay, so there's one more issue that I want to talk about. It has to do with something we're going to call the sign conventions involved with defining angular velocity and angular momentum. So there's a little bit of an issue that arises that's sort of didn't really arise in the linear case. So if you have an object that is constrained to move linearly back and forth along a straight line, there are really only two choices for the direction of that we are going to associate with a velocity and a linear momentum. And it's pretty obvious that the direction of the velocity and the momentum is going to be the direction in which it's moving in, right? If it's moving to the right, we're going to say it has a momentum directed to the right and a velocity directed to the right. If it's moving to the left, that's going to be the direction of the velocity and the momentum. But it's a little bit less clear when you have a rotating object how to associate a direction with it. Because, first of all, every point on the wheel at any one time is moving in a different direction. The only really unique directions are the directions along the axis of rotation, and you can either point one way or the other. And so you need some sort of convention to say if a bike wheel is spinning one way, what direction is the angular momentum going to be in? And that's where this so-called right-hand rule comes in. And physicists are very fond of right-hand rules, and we'll see a number of them before the term is done. But here's a simple one. If you want to know the direction of the angular velocity and the angular momentum associated with a rotating bike wheel, again, the axis of rotation is fixed. So really the only choices are, does it point this way or does it point that way? Well, the rule is you take the fingers of you take your right hand. That's the most important thing, is you make sure you use the right hand for doing this. Otherwise, you'll get it exactly wrong. And if you curl the fingers of your right hand along with the direction in which the wheel is rotating, then your thumb will point in the direction of the omega. And since we get the angular momentum by multiplying the angular velocity by the rotational inertia, L, the angular momentum, will also point in that same direction as is being shown in this figure. And then that also gives us, this rule here gives us also a way of defining the direction of a torque. So if you think about how you get a bike wheel to spin, if it's starting at rest and it starts spinning and developing angular momentum along this direction, this relationship says that you must have exerted a torque that points in that same direction. So we'll talk more about the direction of angular momentum and torque next time. But for now, in this one-dimensional world, this is really all that we need to say. And this understanding is sort of the basis for understanding what is being discussed in the demonstration of somebody standing on a platform with a spinning bike wheel. Okay, so once again, I'm going to rely on a video clip, this one prepared by our friends at the MIT Physics Department, who do this demonstration and say it far more eloquently than I could. So let me turn the floor over to the good folks at MIT.
The wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at the negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at the negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
Wonderfully said. And we'll have a lot more to say about angular momentum next time. But for now, that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.